What problem does the MBRL method aim to solve?
The MBRL method aims to solve the problem of sample inefficiency in reinforcement learning (RL) algorithms. Traditional RL algorithms, such as those using complex simulators, can take days or even weeks to train and require millions of trajectories to master a task. MBRL, or model-based reinforcement learning, addresses this issue by allowing the agent to learn the dynamics of the environment without direct interaction, making training more efficient. MBRL methods, like Dreamer and its variants, follow a structured approach involving representation learning, dynamics and reward learning, and policy learning. However, these methods can suffer from sample inefficiency, requiring impractical amounts of gameplay time ranging from months to thousands of years due to inaccuracies in the learned world model. MBRL methods aim to improve decision-making accuracy and efficiency by utilizing learned models for safe and accurate decision-making without the need for extensive real-world interactions or simulations.
How does Dreamer v3 differ from past models like Dreamer v1 and Dreamer v2 in terms of advancements?
Dreamer v3 differs from past models like Dreamer v1 and Dreamer v2 in terms of advancements by incorporating SimLog predictions and various regularization techniques aimed at stabilizing learning across diverse environments. Additionally, Dreamer v3 surpasses the performance of past models across a wide range of tasks while using fixed hyperparameters. Dreamer v3 also addresses the issue of sample inefficiency that plagues Dreamer models by improving training efficiency. Unlike its predecessors, Dreamer v3 achieves better sample efficiency and scalability by utilizing a discrete latent space for modeling the dynamics. Moreover, Dreamer v3 builds on the advancements of Dreamer v2 by introducing new techniques to enhance stability in learning across different environments. These advancements in Dreamer v3 contribute to its superior performance and effectiveness in mastering tasks compared to Dreamer v1 and Dreamer v2.
Explain the step-by-step process of the representation learning in the DART model.
In the DART model, the representation learning process involves several steps. Firstly, the observation space is modeled as a discrete set using a VQVAE. At each time step, the observation from the environment is encoded by an image encoder into a continuous latent space. This encoder is implemented using a CNN. The quantization process then maps the continuous latent space to a discrete latent space by finding the closest embedding vector in a codebook from a set of codes. These discrete latent codes are passed to a decoder, which reconstructs the input data. The training of the VQVAE includes minimizing the reconstruction loss to align input and reconstructed images, minimizing the codebook loss to encourage the embedding vector to be close to the encoder output, and using a commitment loss to ensure the encoder output is close to the nearest codebook vector. Additionally, a perceptual loss is computed to capture high-level features. The total loss in the VQVAE is a weighted sum of these loss functions. This approach enables the modeling of fine-grained, low-level information within the input image as a set of discrete latent codes.
What is the main contribution of the DART model compared to IRIS in terms of policy learning?
The main contribution of the DART model, compared to IRIS in terms of policy learning, is the utilization of transformers for both world and policy modeling. DART employs a transformer decoder architecture, similar to the GPT framework for world modeling, and a transformer encoder, akin to the VIT architecture for policy learning. This approach allows DART to focus on fine-grained details and task-specific features, enhancing decision-making precision. Additionally, DART introduces a novel mechanism for memory modeling using a self-attention mechanism, which aggregates task-relevant information over time. This method improves interpretability and sample efficiency in policy learning. By leveraging transformers for both world and policy modeling, using discrete representations, and incorporating memory modeling, DART surpasses IRIS in policy learning by enhancing decision-making accuracy and efficiency, leading to improved performance across a variety of Atari games.
How is the policy trained in the DART model? And why is memory modeling necessary?
In the DART model, the policy is trained within the world model using a transformer encoder architecture based on VIT. At each time step, the policy processes the current observation as discrete tokens received from the world model. These tokens are extended with additional learnable embeddings, including a CLS token for aggregating information and a MEM token for accumulating information from previous time steps. The MEM token acts as a memory unit, essential for aggregating task-relevant information over time using a self-attention mechanism. Memory modeling is necessary in the DART model to address the challenge of partial observability in reinforcement learning. By aggregating information from past time steps, the model can retain crucial details about the environment, such as trajectories of moving objects or the velocity of surrounding elements. This enables the agent to make informed decisions based on historical context, enhancing its ability to plan and act effectively in dynamic and complex environments. Memory modeling also helps in addressing long-term dependencies and improving decision-making by providing a comprehensive understanding of the environment state over time, ultimately leading to enhanced performance and sample efficiency in Atari games.
Can you explain the significance of utilizing transformers in the DART model for both world and policy modeling?
The significance of utilizing transformers in the DART model for both world and policy modeling lies in their ability to capture long-range dependencies efficiently, which is crucial in reinforcement learning scenarios. Transformers have shown effectiveness in capturing complex relationships in various tasks like natural language processing and computer vision, making them suitable for modeling dynamics in model-based reinforcement learning, MBRL. By employing a transformer-based world model, DART can accurately predict future states, rewards, and episode terminations, enhancing decision-making capabilities. Additionally, transformers allow DART to focus on fine-grained details through discrete representations, improving precision in policy learning. The transformer encoder used for policy learning enables DART to attend to task-relevant cues, aiding in optimal decision-making. Moreover, transformers facilitate memory modeling without the need for recurrent networks, enhancing interpretability and sample efficiency. Overall, the use of transformers in DART enhances its performance on the Atari 100K benchmark, showcasing state-of-the-art results and achieving superhuman performance in multiple games.